Without further ado, I'm going to introduce our next speaker, John Scott. John is the currently serving as the principal technologist for power and energy storage in STMD at NASA headquarters. After beginning his aerospace career in propulsion, Mr. Scott has served as NASA's JSC for over 30 years in engineering, project management, and supervisory positions in support of Space Shuttle, ISS, Orion, and various human exploration study programs. Immediately prior to his current posting, he served as Chief of Energy Convergent Branch and as Chief Technologist in the Propulsion and Power Division at NASA JSC. As Principal Technologist and as Senior Leader, John leads a nationwide team in advancing power and energy storage technologies needed to accomplish NASA's goals for space exploration to accelerate the growth of the commercial space industry. Received his BS in Mechanical Engineering from Rice and his Master's in Mechanical Engineering and MBA from UCLA. And we see your slides. Go ahead and take it away, John.
Well, thanks so much, Matt, and thanks for. I'm flattered that you thought my biography was well written enough to where you just read from it. I appreciate that. Yes, okay. So I'm going to talk about the Moon to Mars program's view of the need for reliability for lunar surface power infrastructure. NASA's leading humanity back to the moon, and doing that in the Moon to Mars campaign. Now, the first steps are human presence on the moon being established, where we practice for Mars exploration, and then on to set up a framework for demonstrate a framework for future exploration by working on Mars. This is a big picture of it. Somewhat more focused picture has to do with the Moon to Mars objectives that were published. They were in work for a good year, but they were first formally published back in April. 4 steps to this, four portions of this strategy of this Moon to Mars architecture: the human lunar return. That's the Artemis mission that's going to give of course, the next man and first woman on the lunar surface. The foundational exploration, sustained lunar evolution, and then on the humans to Mars. Now, there's objectives for infrastructure that have been defined over the course of developing these architecture options. And I'm proud to say that the number one priority for infrastructure on the moon is developing an industrial scale lunar power generation and distribution system, a lunar power grid. The first number one priority for Mars is developing a surface power sufficient for initial exploration on Mars. All right. So those are very important. So again, the agency recognizes that power is about the most important thing we can be working on in the infrastructure to support the Moon to Mars campaign. Now, there's something else that I want to remind everyone of. The moon exploration, the lunar exploration campaign is starting on the pole rather than the equator where the Apollo missions went. There's a reason for that. The equator of the moon is the easiest place to get to in terms of propulsive energy, in terms of delta V. The pole is much harder that way. However, since we're talking about a sustained presence on the moon, the pole has much better access to solar illumination. So it's that reason that our exploration campaign is being set up to start at the lunar pole, in the lunar South Pole, because of the availability of solar illumination for a greater part of a month. The presence that's been noted of volatiles in the permanently sheltered regions, the ice in the craters, is a little something extra, a lagniappe. The reason we're going there is because of this illumination, the illumination availability at the South Pole. Now, of course, while we're at the South Pole, the key app, the killer app, if you will, for surface power is ISRU, in situ resource utilization. The business of supporting human presence on the moon will be a relatively small portion of the power demand. The main demand is going to be from the production of propellant on the lunar surface, from lunar surface resources, mining construction materials, and so on and so forth, which could go on to a rather large-scale effort. It's supporting this activity, the ISRU activity, is really why we're building a power infrastructure. That's the ultimate goal of it. Now, with this in mind, we have a vision for how the lunar power infrastructure might be growing. Well, we've got 3 phases defined, and they're rather arbitrary. First is the Artemis campaign elements themselves. That's the landers, the rovers, the lab modules, the HAB modules, manifested on the Artemis campaign. The power architecture of that is going to be done by NASA. It's NASA-led, and is basically a human spacecraft, a human exploration mission throughout the Artemis campaign. NASA is the system architect, and the idea is that we've got relatively short transmission segments. The power demand, each module might be 3 kilowatts, maybe 40 per camp. We used to call that base camp, or maybe cluster is a better word, but that is another connotation that I don't want to use. But this gathering of Artemis elements might add up to 40 kilowatts, but there could be several of these gatherings across the lunar surface. And some or all of these may or may not have a demand for an external power augmentation. Okay, that's the Artemis element of this. Oh, I should remember this chart. Notice its logarithmic scale. It's got transmission distance on the abscissa and power level on the ordinate. Notice also there are no dates. All right. So the only input to this that has any dates at all is the Artemis campaign manifest. The rest of this does not. Now, once we do the Artemis as the Artemis campaign gets going, there's to be a handoff from a NASA architect for the power system to an industry architect for the power system. This handoff to a commercial lead. The first maturity of that we're calling phase alpha, and you can see that illustrated here. Industry's leading this. Industry's paying for this. Is a key thing to point out. Or private capital will be paying for this. The arbitrary goal for maturity of this is 2,000 metric tons a year of ISOU propellant production, and we think that might take multi-kilometer transmission segments for a total of 2 megawatts of power. It's about 2 megawatts to produce 2,000 metric tons a year. That's regardless of how you produce it. So that's phase alpha. Going on to a global lunar power infrastructure, we're calling phase omega. Industry still is a system architect, and that's all about building facilities from in situ materials, building more products by ISOU processes, 1,000 kilometers transmission segments, a gigawatt total, a small city, the equivalent. The main distinction between phase alpha and phase omega is, besides anticipated scale, is that for phase omega, we think we'll get into actually producing the power system components from lunar regolith, conductors from aluminum refined from the lunar regolith, PV arrays printed from lunar silica, and so on and so forth. So that's the general evolution. Again, the foundational exploration, humans to Mars segments of the architecture will be run by the Artemis campaign. The sustained lunar evolution is really a function of these phase alpha and omega industry-driven, private capital-driven expansions. Now, this is one possible end state, is the term they use, that the Artemis campaign might leave us with. And again, there could be several of these, but it's a collection of modules that are crude modules. And there's the mobile assets as well. And these will be, wired together. The power system architecture will be crude spacecraft fault tolerance, and that we anticipate managing this as we have any other crude spacecraft, just somewhat longer transmission. But it's important to note that the transmission distances within this cluster of elements is short enough to where we'll maintain our historic 120 volt or around 120 volt power standards. There's the power standard for the gateway element has been developed from the space station, and it's about 120 volts DC. So that's the kind of power network we're talking about. If there becomes a demand for external augmentation of all this power, each of these modules has their own power sources. That's an important thing to point out. If there's an external augmentation, that might come from a power tower somewhere, might come from a nuclear power plant that's of course being developed at some expense. But those may or may not become part of the Artemis architecture. All right, but that's an option for future growth. And so now that's where Artemis leaves us. The phase alpha gets much larger. We're talking again, a multi-kilometer transmission lengths, which will perforce lead us to kilovolt scale transmission. It may be AC, it may be DC. The trade between that is part of what we need reliability estimates to make. All right, but these will be, these could come from farms of vertical solar arrays on the moon. There'll be, storage out there, grid level storage. The fission power plant could be part of this. And the power is going to a set of ISOU production facilities spread across the lunar surface, and also beaming power down into the PSRs for ice mining to the extent that is developed further. Note also, this could be providing external augmentation power to several Artemis clusters. Now, this is a very ambitious program. We're very proud of it, but it's not going to do us any good. All this power technology is not going to do us any good if the whole thing goes dark on the first solar minimum. That's why we're having this workshop. We're worried about that. And the reason we're worried about that is a combination of two things: high voltage power transmission and the lunar radiation environment. Now, here's why that's a problem. The cislunar space systems, anything operating in cislunar space doesn't benefit from the shielding of the energetic heavy ions that come out of solar storms or come out of cosmic rays that takes place in the Earth's magnetic field. You can see from this chart, it doesn't look like there's a big difference between the solar particle, let's say in this case, a solar particle event, between that, across the range of energy transfers. However, that's an order of magnitude or more. So that's enough to matter, we think, in the system reliability. How this affects things comes to the interaction of these heavy ions with wide bandgap semiconductors. This is technology that pervades industry, the industrial power industry, and aerospace. Their Achilles heel is the effect of a heavy ion and a single event effect. Single event latch up, single event burnout. Those can all be quite catastrophic for these devices. And so how you manage this matters in overall system reliability. You can make, there's trade-offs between different materials you can select for the semiconductors. They can, usually if you're more rad hard, you're less efficient. So there's a trade-off there. It's a difficult thing to prove. And again, there are things rated as being rad hard, but they're vastly derated from the blocking voltage that they might otherwise be able to do, and it makes them less efficient. So we're not quite sure all the time what rad hard means. That's something that we have to understand. So with this combination, again, high voltage and the need for power, the way power electronics react to the environment in cislunar space means we have to pay attention to this. This is where we're going to get bit. And again, that's why we're starting this, what may be a series of workshops about power system reliability. This is what concerns us. Back a little history, go back to how the human spaceflight reliability for power systems has been done. It's really all based on, historically based on fault tolerance. The historic crewed spacecraft, even up to the ISS, we didn't rely on reliability assessments that the previous speaker just discussed very much for its design. It was a historically based redundancy, essentially. The Artemis program, though, which we'll hear a little bit longer, is actually able to, there's enough database for the way, relatively low voltage systems behave at least in the low Earth orbit environment, to where we think we can do some PRAs and prior reliability assessments and use those to negotiate lock-on requirements. You'll hear more about that later, and have that set up as a design requirement for the.
I think
Hello, folks.
we might have just lost John, everybody. John, if you can hear us, you might need to log out and log back in, because you seem to have frozen and we lost your audio. So hopefully we can get John back very quickly, and we apologize for the technical issues, everyone. Just give us 1 second here.
We could try a dissimilar redundancy and have someone else try to give John's time.
Hey, I'm back on.
There we go.
Hey, that's not bad. That's not bad. That's pretty quick to being up again.
Because my internet came on, and I'm on Roger Boyer's link for some reason. But anyway, okay, I see you got me still on. You've got me still on chart number 12.
I do.
All right. Okay. Well, I'll try to speed things along a little bit here. I'm just trying to make the point that the Artemis campaign elements, we network together using basically the same kind of assumptions that we're using for lock-long calculations, using redundancy for the Artemis flight elements. Now, when we're talking about the phase alpha, we're in a different situation. Could have a multi-gigawatt scale eventually. Well, they can have a multi-megawatt scale. So terrestrial, we'll have to act like a terrestrial power grid, which you're going to hear about some more later. The reliability of the grid will hinge on the reliability of those converters, which again is affected by the environment and the fact that we're operating at high voltage in a way that we haven't dealt with before. All right, so we in the aerospace industry have not dealt with before. So it's we've got a lot of thinking to do to figure out how to measure the reliability and how to even set requirements for it. I mean, one could go and think, we'll just make everything redundant like we do for a spacecraft. But if you look at the cost of the infrastructure, I don't think industry, the users, the ISRU plants are going to want to pay for that. Again, so we'll have to negotiate requirements, between power system and the industrial users, similar to that is done for terrestrial power grids, and that's been done based on standards that have developed over a century. So what we're going to have to do, an action I'm giving to LSIC here, and I'd like to give to them, is down in this corner. We develop a resource exploration acquisition team between the LSIC power and ISRU focus groups to define the interface power quality and power feed reliability requirements for these ISRU production facilities, and develop consensus tools to assess and verify compliance with that reliability. That's a few words under what I think is a very complex task. So I'll get off the stage here. The moon's always been a subject of fascination for mankind. The earliest human texts will often discuss it as if it's my slides haven't moved. We'll often discuss it as if it's a source of, usually it's a sign or a lie, but sometimes it's a source of riches. It was never seen as a place or a thing. Now, by 1865, when Jules Verne wrote the book that kicked off the space age, the moon was recognized as being a thing, a rock, and being a place. But thoughtful people still thought there might be life up there. And actually, that was the impetus for Jules Verne's novel. It was going to see about that. There wasn't, of course, life on the moon, except for a brief visit around the time of the centennial of this book. But if we do tasks like this correctly, maybe by the time of the bicentennial of Mr. Verne's book, we will, that will be true. Thank you all so much for your kind attention, and sorry about the dropout.
Thanks so much, John. No, it worked out, and we have some padding in the schedule, so we'll still go ahead and take a few questions before we move on to our next presenter. So thanks again, John. We have a question here from Hunter Williams in the chat, and if someone else has a question, feel free to go ahead and type it into the Q&A feature. Hunter asks, has the Artemis campaign office indicated interest in reliance on using commercial power grid for any of the funded Artemis missions?
Oh, that's a brutal question, and the key brutality is in use of the term reliance. Now, so I'm being a little bit facetious. If you look at the lunar architecture teams, it's an Artemis campaign group. There's studies. There's many end states they define. The one I showed in my earlier charts is somewhat that's one of the more ambitious ones. Where is it? Okay, one of the more ambitious end states, and so it ends up being so again they're allowing for the potential of it in their some of their end states that it might become usable. Well, what it does for any of the Artemis campaign requirements, it having external power that might come from an external power grid from a commercial provider opens up your location options. You don't have to necessarily find the sun to keep the they say the lab or hab module solar arrays fully lit all the time, and you can have a better time surviving the night. But again, reliance, no. We're not. I don't think they would say that at all. They were certainly are allowing for that being available as an option.
Thanks, John. I'm going to promote one more question in the chat here.
Mhm.
The question is, what year will you need the power grid developed on the moon to support the initial Artemis missions?
The initial Artemis missions don't need a power grid at all. You know,
And then,
again, the point is that they're self-sustaining in power. Now, of course, you know, as we're getting more into it, look at the, you know, that some of the first assets, the LTVs, for example, they're supposed to be able to have traverses across the lunar surface. And depending on how you estimate those, and especially when you consider the uncertainty we have in the elevations around the lunar pole, they may not, and the amount of storage they can carry, they may not be able to do any more and chase the sun. So again, there might need to be some external power source, but that external power source might come from a lander, its solar arrays, or the solar arrays on a HAB or a lab module. So again, the initial Artemis missions, you know, especially human lunar return, and the ones immediately after that, are intended to be power self-reliant. And of course, and what that means is that that does restrict where you'll place them. You know, there are some eternal light spots. So another question on the lunar pole. We could try to place it there. Again, those decisions have not been made. But again, you know, the initial Artemis missions are trying not to use external power for those elements at all.
thanks, John. Yeah, I see you addressed Chris's question as well. Let's do one more question before we move on to Blanca, because we're only a couple minutes behind schedule and we can make that up. Dennis asks, if NASA is going to open up the possibility of using commercial power, we need a cost point, dollars per watts, to begin developing business plans. So I think it's just interested in your feedback on that.
Yeah, well, I'm sure you do. And I think when you say a cost point, I think what you mean is a demand signal. You know, how much power is NASA going to be willing to pay for? And I think we are just about proscribed from giving that number. We really can't predict it. What NASA's job is in enabling the commercial, the phase alpha, what I've called phase alpha for power, just the lunar sustainability, the lunar presence in general, is to de-risk the technology required and the operations required. STMD is funding a bunch of technology projects, you know, some of which come up in these charts. The job of those is to de-risk the technology you need for the building blocks for this commercial power system and the ISRU system, all right, the ISRU production system. The Artemis campaign's job is to de-risk the operations of it, actually show that it's possible to land one module kind of near another and connect them. You know, that is something what the Artemis campaign, I think, is obliged to do. And the other thing you need to make this, that's needed to make this commercial power grid happen, is funded by private capital, essentially, is for a demand signal to come from somewhere else. Because NASA is not going to give that demand signal in terms of how much power or how much ISRU. That's my perspective on it. And I'll see if I get any feedback from senior management for saying that wrong. But I think that's the position we're in.
Well, I think you said it perfectly, John, and hopefully we can discuss this more later in the breakout sessions. John will be in the breakout sessions.